Bismillahirrahmanirrahim. Assalamu alaikum dear students. I welcome you to the next session of the Linux lecture series. Today we're going to look behind the curtain and we will try to understand certain data structures used by different UNIX file systems for the management of files. Dear students, I strongly recommend that before taking this lecture you should see the videos of disk geometry, disk partitioning and disk formatting to get the best out of this video lecture. Alright, let's start playing. Right, gentlemen, this is the schematic view of the UNIX file system. We have discussed this view in the disk partitioning lecture as well. I will just brush up a little. So, this view in front of us is the linear view of a hard disk with the MBR partitioning scheme placed at the 0 sector. This is the 0 sector of this. And within this 0 sector, we all know that the initial 446 bytes contains the stage 1 bootloader. And after that, there are basically 4 entries over here. Each entry of 16 bytes to keep track of the 4 primary partitions. This scheme tells us that we have 3 primary partitions, 1, 2 and 3, and the rest of the area is managed by an extended partition. And within that extended partition, we further are having 4 logical partitions. And we know that the first logical partition starts from number 5. The enlarged view of one of the primary partition is also shown over here. In this partition, gentlemen, there can be a lot of data blocks over here. Every file can be composed of at least one or maybe many data blocks. After these data blocks, you can see a lot of inode blocks as well. Every file has one inode block associated with it and an inode number as well. Every file has an inode number. The inode uniquely identifies a file within a partition or within a file system. You can say that the inode is to file system the same way as the PID is to a process. And each inode number has a space, a block over here, which is known as the inode block. Well, this inode block contains the metadata about the file. The metadata about the file like the name of the owner, the group, different timestamps, size of the file, permissions, and many more. Right, gentlemen, the operating system maintains an inode table as well. There is an inode table as well. And this inode table contains information about the total number of inodes, the inodes that are used, the inodes that are free. Let us move on to the terminal and run a command so that we can have a fair idea of. Let me use disk free with a -i option on div sta1. So this command shows you that this file system has total of this much inodes. This much inodes have been used so far. This much are free. The inode usage is about 34% and they are mounted on the / root partition. We can always see the inode numbers using the ls command with a -i option. And if I want to see the inode of a directory, I use D with that. So / has inode number of 2. Within /, let's suppose home has an inode number of 130561 on my system. And within home, the directory Arif has the inode number this. And within Arif, we have lot of files. Let's suppose I talk about a file arif.arif, which has inode number of this. So we have inode numbers associated with each file. So after seeing the data blocks and the inode blocks, let's move on to these two things. The boot block. The boot block is basically a portion where stage 2 bootloader of the operating system resides. And this happens only if this is a bootable partition. If this is not a bootable partition, it will be empty over here. Then we have the super block. This SP is the super block. A super block contains a very important information like for example, the file system of this partition, then block size. Is it just 512 bytes as is the sector, or it is 4 KB, whatever. Then it has information about the free blocks or the unallocated blocks, and it has information about all the inodes which we have just seen. And let me use a command on the terminal to show you a list of these as well. And the command is tune to fs. Yes, tune to fs. So tune to fs is used to tune a tunable file system, basically the ext2, ext3, and ext4. And if you want to see, I think need to use sudo with this. And let me see the long listing with the device DEVSDA1. Let me get the password. A lot of information, so let me pipe it to less. Okay, so this is showing a lot of plethora of information like the file system volume name, the label which I have given it to Arif007 in some previous lecture, mounted on the UUID, universally unique identification number, the magic number of this partition, which we know is there in the last 2 bytes of the boot partition or the MBR. Then we have the revision numbers, and then file system state is clear. Yes, over here we have the inode count, block count, free blocks, the first block, and a lot of information. Yes, block size is important. We have 4096 bytes of block size, and the mount time and the last write time. A lot of information you can see over here. Okay, so this all information is there in the super block. So this is actually the super block which is going to manage this entire partition. It's going to allocate and deallocate blocks and keep track of all the free space as well for all the files. Okay, let me move ahead. Okay, right, gentlemen, this is the structure of an inode block. As we have talked about the inode number and an associated inode block. This structure is associated with a file. And we know that everything is a file, so every file has an associated inode block, which contains the metadata of the file. Like you can see the permissions, the timestamps, and we know that there are 3 different timestamps that the Linux system maintains. One is the A time, that is the access time. There's the M time, the modification time, and the C time, the last status change time, and the owners and the size of the file and so on. But right now I'm interested in digging out information of how come the operating system finds out that what all data blocks are associated with a particular file. Right, gentlemen, there are about 13 pointers in this structure. You can see with the yellow portion there are 10 pointers over here. Then we have the 11th pointer over here, the 12th pointer which is double indirect, and the 13th pointer which is the triple indirect pointer. So these 10 direct pointers points to 10 data blocks. These are the data blocks. If a file comprises of only one data block, so only one pointer is used, and if the file is large, it can occupy up to these 10 data blocks. If the file grows and it's more large, then the system can use the single indirect pointer. This single indirect pointer basically do not point to a data block, rather it points to a block which contains again the pointers. And these pointers again point to the data blocks. We have over here data blocks. Just try to understand. Let's suppose that the block size is 4 KB. Block size is 4 KB. And let's suppose that the pointer size, the disk pointer size is of 4 bytes. So that means this block can contains 1K pointers. So we have 1K data blocks over here at this level. We have 10 blocks over here. We have 1K data blocks over here. Similarly, we have a double indirect pointer. This double indirect pointer points to a block which contains pointers, and these pointers further point to blocks which points to data blocks. So we have about 1K blocks over here which points to 1K square data blocks. In the same fashion, in the triple indirect pointers we have 1K cube data blocks. So if you want me to calculate max file size support with this architecture, I will take red color and I will say that 10 direct pointers blocks plus 1024 the data blocks which are pointed to by the single indirect pointer plus 1024 square pointed to by double indirect plus 1024 cube pointed to by the triple indirect pointer. So you sum up these values and this much data blocks, and if a data blocks is of 4 KB, you can multiply it with 4 KB. So this is the inode block structure of inode, and you can well understand that it is very powerful. Performance is good for the small files, and still you can have large files with you. Right, gentlemen, if you want to dig out information about the inode block of file, there are different commands you can use like ILS, inode list, icat, istat, and of course the famous stat as well. Let me use one of these commands on the shell for better understanding. Let's suppose that we have an empty file over here. Do we have an empty file over here? Yes, we have an empty file. No, this is not empty, it has some size. Let me say touch, let me rm empty file, let me touch empty file, and let me see the size of this empty file now. Of course, the size is 0 now. So this is an empty file. So let me stat this file, stat empty file. Let me shrink it. You can see once I give this command stat empty file, it tells me the name of the file, the size of the file, the blocks it is occupying. Since it is empty, so it is not occupying any block. The IO block size, which is 4 KB, which is a regular file, the device, the inode number, the links, the access permissions, the UID, GID, and of course the 3 timestamps. And if I write something in this file, echo learning Linux is fun with Arif. Let me redirect this to empty file, and let me repeat the above command now, stat empty file. So now this time you see that it is no more an empty file. This is a regular file, it's not empty, and it has 8 blocks associated with it, 512 bytes of block. That means whenever you write something in a file, its size, the size allocated to it at least the 1 block, and that is 4 KB. On the contrary, if you use ls-l with this, you just see the number of bytes which I have written, that is 37, including the last end of file character. But over here we have 8 blocks. The size is of course 37. Okay, so the way we can stat a file, we can stat a partition or file system as well. Let me clear stat -f option to div sta1. So this time it tells you information about this particular file system, and it says the block size in this file system is 4096, fundamental block size is the same, and total number of blocks are this much number of blocks are free, this much are available, and so on. So total inodes and free inodes. So you can get the information from here. Okay, fine. So let's move ahead and let's see. Okay, so now since we have understood how the data blocks and the inode blocks are managed within the system, let's see the file system in action. Let's try to understand what actually happens when a user creates a file. Let's suppose that the user gives this echo command, and he writes this in this file, /home/arif f1. f1 is the file which is located in the directory Arif, which is there in home and which is there in /. So what actually happened is the operating system kernel 4 main operations. The 4 main operations the operating system kernel perform are, first of all, it stores files metadata. In a free inode block, and it has searched for a free inode block. Let's suppose it is 47. So the metadata is stored in this file, and of course at the end it stores the pointer to the data block as well. Let me say record the address of data block. Maybe 1, maybe more. If there are 10, we can use direct pointers. If there are more than 10, we can use the single indirect pointers, or maybe for very large files, we can use double as well as the triple indirect pointers. The third thing is stores the file's data in data block. There may be 1 or more. And the last important thing is that it adds an entry in the parent directory. And over here the parent directory is /home/arif. So before, okay, let me tell you about what a directory actually is. So gentlemen, a directory is a special kind of file managed by the kernel. It is a special kind of file managed by the kernel, and it contains entries. And in one entry of this directory, you find an inode number with a corresponding file name. So the entry of a directory contains inode number and file name. So if this is Arif directory, it contains the file f1 with a corresponding inode number, and it may contain a file f2 with a corresponding inode number, and it may contain a subdirectory d1 with a corresponding inode number, and so on. A user can write a directory by creating a new entry in it. Once you do touch, or you do vim, or you do mkdir, or you use any program to create a file, any type of file within a subdirectory, within a directory, an entry is created in that file. So this is how a user writes a directory. And a user can read a directory by reading the contents of that directory. For example, if I want to find out that whether the Arif directory has a file f2, so I can read the contents of the directory. So by reading the contents of the directory, I can read the name of the file as well as the corresponding inode number as well. Okay, gentlemen, if you have understood the idea of creating a file, let's move ahead and see how we can read a file. So this is a bit important, and let's try to understand it. Let's suppose I run a command. I run this command which says I want to see something from / directory, home directory, Arif directory, and then we have f1. So actually what happens is that first of all the cat program tries to read the / directory, and the cat program reads the / directory. It goes to the inode number 2. It knows that the / directory has inode number 2, and within the inode block the cat program sees whether it has permissions to read this directory. If yes, it searches this directory. It searches this directory for another entry named home, HOME, home. It has find home. Now it sees the inode number of this home, which is 561. Then the cat program opens the directory 561, and before opening the directory 561, it searches for the inode number 561 and sees the inode block of this inode and checks out whether the cat program has permission to read the home directory. If it has permission to read the home directory, it searches this directory with a file name Arif. So after it finds out Arif over here, it sees the inode number 533, searches for this inode number 533 and sees the permission. And if it has permissions to read this directory, which is Arif, it goes through this directory and searches for a file named f1. And if it is successful, it finds the inode number of this file, which is 615, opens the inode block 615, checks if it has read permissions on this, and then read the contents of this file and display on the stdout. So this is how a cat program searches for a particular file within the UNIX file directories. Let me have a short break for Azan. Okay, gentlemen, welcome after the short break of Azan. So we talked about how the file system can read a file. Let me review again. We have the / directory. The cat program first sees whether it has permission on this directory. If it has, it searches for home, its inode number, and find out that inode number and the inode block, searches if it has permissions on this home directory. If it has, reads this directory, find out the inode number of Arif. Inode block of Arif is read, brought into memory, reads it. If it has permissions on the Arif directory, reads this directory and finds F1 having the inode number of 615. Bring the inode block 615 in memory, and if it has permission of reading the file F1, it opens this file, read its content and display it on std out for you. One more thing, gentlemen, you can see in every directory you have two files, one is dot and the other is double dot, and it is only the / root directory which has the parent as well as the current pointer pointing to the same location, that is inode number 2. Since home is a child of root directory, so at the parent part it has inode number of 2, and in the current working directory it has the inode number of 561, which is mapped onto this. Sorry for destroying it. Similarly, Arif has its own inode number of 533, and the parent inode number is 561, which is the inode number of home. So every directory has a pointer to its parent, and every parent directory has pointer to its child. So this way the traversing is normally performed. Okay, fine, gentlemen, let us move ahead now. Now we have understood how files are managed, how they are kept on the disk. Let's see how they are managed in the memory by the operating system. And this is the slide which you might have seen before as well, the famous per process file descriptor table. And this is a table for every process. Every process has at least 3 descriptors opened at a time. Descriptors 0, 1, 2 and 0, 1 and 2. 0 points to std in, 1 points to std out, and 2 points to std error. And if a process opens any other file, it starts from the file descriptor 3. So these are the file descriptors. The maximum number of files which a process can open depend upon a variable, that is open max. And every entry within this points to an entry inside the system-wide file table. This is a system-wide file table. The kernel maintains a single system-wide file table for all the open file descriptors, and the maximum number of entries in this table are the maximum number of files which can be opened by the OS at any instant of time. This system-wide file table contains many flags like the current file offset, which is changed by the reading, writing, or the lseek system call. It contains a flag which tells you that what is the file access mode, whether it is read only, write only, or read write. And there are other flags as well in the system-wide file table like appends, synchronous, reading, writing, or non-blocking I/O. Finally, it has a pointer which points to the inode table, and this is the inode table which we have been talking about in the last about 30 minutes. And every inode table has an inode block, and this inode block contains all the permissions which are checked, and finally it contains a pointer to the address of the data block on the hard disk, and we go onto the hard disk and searches that out for us. Right, gentlemen, let me move on to the shell now and briefly touch upon certain commands. Okay, the first command I will like to touch upon is the df command, that is disk free. The df command displays the amount of disk space available on the file system mentioned. Suppose this is the file system, which is STA1. This is a number of blocks These are the blocks used, these are the available, this is the percentage usage, and this is the mount point on which it is mounted. You can pass an argument to df, for example div sda1, so it will tell you just information about this particular partition, and if you want to know about the current working directory, you can use df give the path of that directory or dot for the present working directory, and since it is mounted on the same root partition, so it gives you the same information. If you want to get information about the inode blocks, you can give -i option. So this time it gives you information about the inodes used, the free inodes, and the percentage usage of those inodes. So disk free is a good command to find out the disk space availability on your system. The next command I want to talk about is the du command, disk usage. The df gives you information about the entire file system, but if you want to know how much space a particular file or a particular directory tree is occupying on disk, then you use the du command. So let me use du with the -h option on @c passwd. So it tells you that it has a size of 4 KB. So let me ls-l @c passwd. So you see it has a size of 3260 bytes. Okay, so let me create a file, touch an empty file. Remember, we already have an empty file, so I have named it an empty file. Let me see the inode numbers. So this is really an empty file because its size is shown 0 over here. Let me use du with this. So you see, if a file is really empty, it is not allocated any data block on the system. But let me write something in it. And let me see. Now it has a size of 4, B, Y, E, and the end of file character. Okay. Now let me use du-h with this. So over here you have now 4 KB. So this is the minimum amount of space that is allocated to any file. Although an empty file has just 4 bytes, but the space allocated to it is 4 KB. Let me do stat as well on this file. And if you stat, its size is 4 bytes, but the number of blocks which are given to it are 8. Okay. So you can run du on a particular directory. Let me run it on my home directory. So it recursively goes and it tells you the total usage of this. And let me see. Okay, I have a documents folder. So this document folder contains not much of things, so its size is just 4. These are the number of blocks which are being given. So this was about the disk. Let me talk about the open file as well. lsof is a very interesting command which lists the open files. ls list of is open files. So it lists the open files. Please read the man page at the time of your convenience. For the time being, let me show you the power of this command. Let me open a file @c passwd. So there is a program which has opened this file, and let me check out the password of this the PID of this program. The PID of this program is 10801. So let me use lsof, and I want to check out what all files this process 10801 has opened. Let me shrink. Oops. Okay. If it is visible to you, it is telling me that the less command, less command has opened this much number of files. I was just thinking that less has opened just the @c passwd file, but the less command has opened this much number of files. For example, the less has opened the less program, bin ls, bin less. Less has opened home Arif because it is the current working directory. Less has opened / because it is the root directory. and Les has opened certain libraries as well, which are shown over here. And things of our interest are these 3 or 4 or 5 entries. So this is the descriptor 0. Okay, let me come up over here. Descriptor 0 on div pts sub2, which is the terminal. We will talk about terminal some other time in detail, inshallah. But we have 0, 1, and 2. These are the 3 FDs which points to the terminal: std in, std out, and std error. And this is for the div tty. And finally, we have etc possibility open at descriptor 4. So gentlemen, this is the FD column, user column, PID column, and device. We will talk about the devices some other time again. And these are the name of the file which this process has opened. Okay, let me tell you another command, that is fuser. Let me load it more. Okay, so fuser basically identifies processes using files or socket. It is used to list the PIDs, the username of the processes who are currently using the specific file. So lsof list open files on stdout, all the open files, or maybe the open files by a particular user, or maybe the open files by a particular PID. So fuser is something else. You give the name of a file to fuser, and you see it tells you that at c passwd this file is opened by a process whose ID is 10801, and of course it is opened by this. Okay, let me zoom, and let me be Kakamana. Yes, I can be Kakamana. And let me open the passwd file. So the passwd file is opened by Kakamana on this terminal, and by Arif on this terminal. And let me call this again, and let me be sudo, so that I should be able to know about all the users who have opened these files. Still it is not. Okay, so actually what should have happened is that I should be seeing the names of those. So maybe I'm missing some option. No, I'm not missing any option. Okay, so let me less by Kakamana as well, and let me run this. Okay, so now fine. Now fuser, I am telling fuser, please tell me who all users as well as processes who have opened this file, and it is telling me that this file is opened by a process 10801, which is being run by Arif, and a process 10852, which is being run by Kakamana. Okay, fine, gentlemen. Let me have a quick review, very quick review of what we have done. So in the very beginning, we have talked about the schematic view of the UNIX file system. We have seen the MBR, the 3 primary and the extended partitions. We have seen the logical view of this. A partition containing the boot block, super block, a lot of inode blocks, and the data blocks. And we have said that the inode is to a file similarly as the PID is to a process. And the super block is basically the block which contains a lot of information regarding the file system, the block size, the free blocks, the inodes, and it manages all those things to allocate blocks to files which are being created, and to free the blocks from the files which are done with that. Okay, then we talked about the structure of an inode block, and we have seen that all the metadata of a file is there in the inode block, and it has 13 pointers which points to the data blocks. And we have a lot of commands over here which you can use to view the contents of the inode, and seeing this we can easily manage to calculate the max size of a file we can have using this structure. Then we have seen the file system in action. We have given a command to create a file, and we have understood that whenever a user creates a file, the kernel stores the file's metadata in an inode block. It stores the file's data in a data block. It records the address of the data blocks in the inode block, and finally it puts an entry inside the parent directory, and that entry normally contains an inode number and the file number. And then we have seen that how a process can carry out the reading of a file, how a process moves from one directory to the other, and finally it reaches the file and display the contents of that file. And finally we have seen that we have the in-memory data structure available to us to keep track of the open files, and that is PPFTT, system-wide file table, and the inode table. And using these structures, UNIX very successfully manages the file system. I hope, gentlemen, this was informative. I wish you all the best and happy learning. Allah Hafiz.